All right, welcome to Chapter 1 on your summer assignment. I'm going to go through the worksheets right now and give some overview of these top level concepts from Chapter 1. These are the mastery objectives for each one of the topics that we'll be covering. These are also listed on the wiki. You'll see these, and you'll also see these. Eventually, I'll scatter these through the PowerPoint presentation as well, so you can track these as we go. First of all, significant digits. Significant digits are used as a method of rounding and also tracking how much precision we have given the accuracy at which we're able to measure our physical quantities using scales or counting devices or whatever. So we have to be careful how we use these because we can't add digits along the way and add precision to a number that doesn't actually exist. So we've got to be careful on rounding, so we'll talk about that. So for each of these items, you should try estimating these yourself. I'm going to actually give you my results for each one of these. So I'm actually going to just make a guesstimate based on my general knowledge. And then I'll actually show you numbers that I actually looked up for each one of these. And there's a natural number of significant digits we use for each of these, and we'll sort of see these as we go along. And so we'll see how many significant digits we use for each. Also, you should make sure that you always show units when you're putting down numbers. If you don't show units on a number, you will certainly hear from me on that on a quiz or a test. You'll lose 1 or 2 points each time you do it, and that can add up really quickly. So don't. And please, when you're writing down units, do not write them out fully like meters. Just use an M for meter. Use the standard abbreviations that you'll see me use in class. Don't waste time writing out all these words. Don't wear up too many pencils. So make sure units are shown. And here's a bonus opportunity, if anybody would like to try to answer this. There are some cases where numbers don't have any units, and you tell me why you would not have units for certain numbers. And you can post your answer for that on our Facebook page. The first person who posts an answer gets 2 points. So my height is approximately 5 to 10 inches or 70 inches. 2 inches. The number of significant digits there, if you look at the 70 inches, that's to the nearest inch. I'm not 60 inches or 80 inches. I'm 70, so that's 69 or whatever. So we've got the number of significant digits is 2. Okay. So I'm rounding to the nearest inch. The number of students at Tyngsboro High School is about 500 students. So my units, I put all my units up here in green. And so that's rounding. It's a really rough approximation to the nearest 100. And so that's a 1-digit number of significant digits. The Tyngsboro population is about 10,000 people. Once again, that's about 1 significant digit. The Massachusetts population, I think it's around 5 million people. And once again, I'm only using 1 significant digit. It's not 6 million, it's not 5 million, it's not 4 million. It's somewhere around 5, not 5.5. I'm not sure beyond the 5. The U.S. population is about 320 million people right now. I think that's pretty accurate. On that number, I'm actually using, that's either 2 or 3, depending. I can't remember the last time I looked at this number. But it's at least 2 digits, the 3 and the 2. It might, the other 0 might be a significant 2, depending on how accurate it is. I would count that as a 2 significant digit. The length of a paper clip is about 1.5 inches. And you notice, like in physics, we tend not to use fractions. We convert to decimals. So it's about 1.5 inches. And that's 2 significant digits. Obviously, that's just a ballpark number I have in mind without actually measuring. The thickness of a paper clip is about 1 millimeter. And that's a 1 significant digit estimate. We're using 1 digit, not 1.1 millimeters, not 0.9 millimeters, 1 millimeter. The length of a meter stick is, well, 1 meter. Well, it's 1 point, actually, I should have 3 zeros on this. It's 1.000 meters, and I'll just add the 0 manually here. Because a meter stick is typically broken down into millimeters. There's 1,000 millimeters per meter. So actually, For this number, I actually have 1, 2, 3, 4 significant digits. All these digits are significant. This is actually a 4 significant digit number that I have. Even though I have zeros there, I know I have precision to that millimeter level, to this digit right here. So meter sticks have accuracy down to a millimeter level. Avogadro's number. Avogadro's number that you use in chemistry, that's how many molecules or atoms per mole of a material. The number you probably use over and over again was 6.02 or maybe 6.022 times 10 to the 24 molecules per mole. The number that I'm showing here has I'm sorry, this is actually 3 significant digits. So I got 1, 2, 3 digits that I'm using. Pi, generally speaking, off the top of your head, you'd probably say pi is 3.14. And so with this particular number, I've rounded it to 3 significant digits. And this goes back to the bonus question I asked before. Notice there are no units on this number. Why is that? All right, so now, on the next page, what I'll do is I'll show you, I looked up all these numbers and I have more precise values for each one. So let's take a look here. And I'm showing you my source as well. So my doctor, here's my source in this column. My doctor actually, they measured me, you could say 5 feet 10 and a half inches. I'm 7.5 inches, so I've increased it by 1. So I've used a more precise instrument and measured it, and I have a better and more accurate estimate. And for Mr. Hook, and actually I just made up this number, this is Mr. Hook, but let's just say he said it's 495 students at Kingsborough High School enrolled right now. In that case, I have actually 3 significant. Before I had 1 with a 500 person estimate, and maybe the number is 495, maybe it's 485, maybe it's 525. But here we have 3 significant. All these numbers here, I looked up on the 2010 U.S. Census. You can actually go online and do this. And they actually do a official count of the people. There's 11,292 people in Kingsborough for the official U.S. Census. Massachusetts population, I was low on my estimate before. There wasn't 5 million, it's actually about 6.5 million. And there are 7 digits in the so this is now I didn't have any question about this. So there's actually 7 significant digits of precision on that number. They count everybody and add them up. The U.S. population, same thing. Now I've added up all the people in the U.S. in 2010 when they did the census. They from every single person added them up, and they have 9 significant digits of information. The length of a paperclip, I didn't change that. I didn't change these. So I can use a caliper. If I use my caliper, though, it's a more precise measuring tool, and maybe the actual number is 1.5632. So I can actually, with calipers, get down to 4 digits past the decimal point. So this would give me a 5 significant digit accuracy. Same thing for the paperclip. Maybe I can use my vernier calipers and find out that it's 1.0137 millimeters. I can have 5 significant digits if I use a very accurate instrument. And length of a meter stick, well, they're crappy meter sticks, so I'd expect that's still going to be stuck at 4 significant digits. It's on this scale. I actually looked up online. This is the National Institute of Standards and Technology for America, and the number that they had posted online had, it's 1, 2, 3, 4, 5, 6, 7 significant digits. And then if you look up pi, if you go to pi.org, it's some sort of a site. I'm assuming some sort of a site. For the last Pi Day, they actually published the first 1 million decimal places, or digits, I guess, of pi. And of course, pi is what we call an irrational number, and it goes on forever and ever and ever. It doesn't repeat. And so the number of actual digits, this is only the first 21 I'm showing here. You can get pi as accurate as you'd like. it'll take you some work and some effort to do it, but you could get an infinite number of significant digits on 5. So, a little example here. Let's say here's my wedding ring. I took it off and I threw it on top of 2 different types of rulers. The metal one is actually what's called the machinist rule, and the plastic is just a cheap ruler you get at Walmart. And which one is more precise? Well, this machinist rule, these things are manufactured with a lot more precision than a cheap plastic one. You can see the lines line up fairly well here. But I can take a measurement with either of these, but the machinist rule I can be a little more accurate, and I can actually interpolate between the spots. You know, if I fall halfway in between, that's half a millimeter, and I can do a little bit of estimating. That's what I did. I said, oh, it's more than halfway, so maybe it's 1.77 centimeters. You can also use other devices. So this is an example of a vernier caliper that measures an inch scale. I actually have some better ones that have dials on it, they're easier to use. And with this, I can measure that it's 1.768 centimeters, which is 4 significant digits. All right, so significant digits. What about using them in rounding? So we started out using our cheap ruler. We had 2 significant digits. All right. With our calipers, we actually have 1, 2, 3, 4 significant digits. Now, here's the trick. If you're doing any mathematics on any numbers, as you do the mathematics, your number of digits, significant digits, first of all, cannot increase because you can't add accuracy by doing math. You can only add accuracy by buying a better piece of equipment to do your measurements. Your overall accuracy is going to be limited to your least accurate measuring instrument. So in this case, let's say I only had 2 significant digits, so maybe I'd have to limit my final answer to only 2 significant digits. For the right case, we have 4 significant digits. So if this is our limiting number, we have 4 significant digits of accuracy for our final rounded answer. If I measure the height, I measured the height here as well, and so later on, if you wanted to calculate the area or volume, you can do that. I'm sticking with the radius and circumference around. And we can finish up these rest of these calculations. But first I said, okay, let's calculate the radius, and I just take the radius. You notice whenever I do a calculation, I write down an equation and I plug into it. So here's my equation. I plug into it. I take 0.017 excuse me, meters. I take 0.017 meters and divide by 2, and I get this should be 0.0085 meters. All right. I started out with 2 significant digits, and I ended up with 2 significant digits. That's fine. I can do that. All right. In the same sense, I took the 0.01768 divided by 2, and I'm sorry, I missed another 0 here. And my final answer is 0.00844 meters. And I have all 4 of these final digits are significant, including this last 0. All right, so I still get to keep my 4 significant digits. Any leading zeros are not significant digits. Those ones don't give you any information about the value of the number. Any ones prior to your first non-zero digit. So these ones are the significant digits. And these ones are the non-significant, any leading zeros. Now let's figure out the circumference. So of course, we all know the circumference equals pi times diameter. Pi is our irrational number, which has an infinite number of significant digits. So if you were to press the pi button on your calculator and take pi times 0.017, you end up getting for a circumference, and this is in meters. Sorry, I left off my units here. I would have deducted a point in my score for doing that. I ended with 0.05340751 meters. All right. Now, problem is, this looks like we have 1, 2, 3, 4, 5, 6, 7, 8, 9 significant digits. But guess what, folks? We only get to use 2. All right. So here are our first 2 significant digits, and what I'll do is I'll look to the 3rd digit after it to do my rounding. So I've got a 53 with a 4 after it. The 4 is below 5, so I will not round to 53. And this will turn into 0.053 meters. I round it properly to 2 significant digits. Which, of course, if you want to convert this to centimeters, I can move the decimal place over twice, which is 5.3 centimeters. So if you wanted to convert it to millimeters, it's 53 millimeters. So that's the circumference of my limb. All right. Now, in the right case here, I used my calipers, which has 4 significant digits. And so now when I multiply pi times the diameter, I get 0.055543358 meters for my calculator because it uses a precise value of pi. But my precision is limited. Here's my limit. I'm limited to 4 significant digits. So I can't go beyond that. Math can't add digits. Right? Only a better measuring device can. I didn't use a better measuring device. All right, so I've got to take my first 4 significant digits and ignore the rest and round to that. So my first 4, I ignore the leading zeros, and here's my first 4. 1, 2, 3, 4 digits. All right, and here's my digit I'll use to round. It's below a 5, so I will not round this. So I'm going to put 0.0554. I'm sorry, I missed the digit here. So 5554 meters. All right. Those are my 4 significant digits properly rounded. And of course, that's 5.554 centimeters, or 55.54 millimeters. All right. So on the right is using calipers. It's a more expensive instrument. It gives you better precision. And here's a cheap ruler. I have less accuracy, less precision. All right, so some rules for significant digits. Any leading zeros don't count when you're counting up your significant digits. So these don't count those. So we have 1, 2 digits for this, 2 significant digits. Any middle zeros do count. So these leading zeros don't count. But here are my significant digits: 1, 2, 3. That middle one does count. All right, so I have 3 significant digits. Ending zeros may count, and sometimes you have to read into the problem to see where this ending zero came from. But if somebody gives me a 0 at the end, I'm going to assume they gave it to me because they actually measured it. So I would argue that if they don't tell you anything else about the problem, then I would probably end up including that as 3 significant digits. All right. But I don't know that I would penalize you on a test for treating it as 2 items. So look for routing work. So, in the example before, I put in some keywords about 500 students. That tells you the number probably rounded or a guess. Almost exactly 500 students. We probably have more precision. Maybe we have 2 significant digits on that. Exactly 500 students. We'd expect all 3 significant digits to come like that. So looking at the wording can give you an idea of how many digits are actually should be included in the count of number of significant digits, especially when you have zeros at the end of the number. How do you treat those? So remember what I said before, when you do calculations, math doesn't add precision. Only if you buy a better instrument does it add precision. So when you do math and you start getting more and more digits on your calculator, you have to go ahead and write down the number, but then round it properly to the smaller number of digits that you have on your least accurate number that you use to start with. So I gave another example here. It says, suppose I run about 5 miles in 34 minutes. So it looks like I have 2 significant digits here and 1 significant digit there. Right? So therefore, my average speed, notice I'm doing a calculation. Whenever I do a calculation, I write down an equation, and I'm plugging into the equation. And then, in this case, I'm also giving a demonstration of how to use proper unit conversions here using cancellation method fractions. So I've got 5 miles every 34 minutes, so I get distance over time. Now, I actually want my answer in miles per hour, so there's 60 minutes in 1 hour. That cancels out my math, so I'm going to get an answer in miles per hour. And when I do this mathematics and I type the numbers in my calculator, I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 digits show up. Now, how many digits should I round this to? Well, I have about 5 miles. That's one significant digit. And I've gotten 34 minutes. That looks like 2. So the least number of significant digits is really what I should round to. So I'm going to round to one significant digit. So really, the only digit that's significant is that one. And I'm going to round based on the one to the right of it. So I have an 8.8. The 0.8 is greater than 0.5, so I'll round up to 9. So it's going to be about 9 miles per hour rounded properly. All right, a little bit of practice here, and this is on your worksheet. So how many significant digits in each one of these numbers? You don't have anything to read into this. You'll just count them up. So I've got 1, 2, 3, 4, 5 in this one. I've got on this one, I'm going to skip the leading 0 here. I've got 1, 2, 3, 4. Remember, zeros in the middle do count. So this would be 4. I'm assuming they gave me 4 digits on this one. On this problem, 9 kilograms. Maybe my little dog weighs 9 kilograms. Or has a mass of 9 kilograms. Excuse me. And so this is actually one significant digit. 9.00. Well, if somebody told me it was 9.00 rather than 9, I'm going to assume that they gave me these 2 extra zeros for a reason. So I'm going to interpret that as 3 significant digits. They must have been using a much better scale. This is actually units for capacitance. So if you study some electricity, you find out about capacitance. These can be very tiny values. And so I've got here, all my leading zeros are not significant. So what I have left is 1, 2, 3, 4, 5 significant digits in that number. All right, 20.25 kilometers, all those digits are significant. Remember, leading zeros are not significant, don't count. Zeros trapped inside are significant. Zeros trapped at the end may be significant. So here I have 4 significant. The other thing to do, let's practice a little bit of rounding. Let's round to 2 significant digits in each case. Well, my 2 significant digits are right here on this first problem, the 1 and the 2. So I'm going to look to the 7 for the rounding. All right, 7 is greater than or equal to 5, so this is going to round up to the 12 is going to go to a 13. So we get 1, 3, the 7 turns into a 0, and that's it. That's 127 rounds up to 130. Here we're rounding for the 0.70. We're looking to the 3 as our rounding digit. That's below a 5, so we get negative 0.70%. 9 kilograms. Well, how can I round that to 2 significant when it's only 1? I can't add precision, so never add precision. Just keep that the same. It's 9 kilograms. Never add precision. All right, I'm rounding this to 2, so here's my 2 digits right here. All right, and so I'm going to use this 0 as my rounding digit. Well, 0 is going to stay 0, so it's going to be rounded to 9.0 kilograms. For the farad one, the capacitance problem, the 18 are my first 2 digits, and I'll look at the 4 right after that. 4 is not a 5. For a 5, I'd round up, but I'm not going to do only 4, so I'm going to keep the 18. So it's a 0 point. How many zeros did I have? 1, 2, 3, 4, 5, 6, 7, 8 zeros. And 18. Better yet would be to put this in SI prefix notation. So I'm going to move this over. There's milli. There's micro if I move the decimal there. Here's nano if I move the decimal there. If I move the decimal there, there's another 0 in here. I get 180 picofarad. 1 of the 18. On this kilometer problem, here's my first 2 digits, and I look to the second 2 here to see if that's my rounding digit, and I'm not going to round up on that one, so I get 20. So why not always use tons and tons of significant digits? Why not just get really good equipment? Well, the equipment costs money. All right, so if you don't need 10 digits of accuracy, you don't want to waste the money on trying to buy it, because accuracy costs money, or precision costs money. For example, to guesstimate that there's 300 million people in the U.S. versus know exactly the 9 digits costs us $13 billion in 2010 to count every person in the United States. On a car, like a Mercedes, for example, They are precisely engineered, much more so than a Yugo. Yugos were in the 1980s really, really junky cars from Yugoslavia that were really, really, really cheap. And the door on a Mercedes, if you've ever ridden a Mercedes and open and close the doors fit perfectly. And they close nicely and easily, and they make a nice seal. Yugo or old American cars in the 70s and 80s, the American cars were pretty lousy. And the doors would all be crooked. They wouldn't shut properly because they weren't machined to very precise standards. All right, making things precise costs money. So Mercedes costs a lot more than Yugos, which have a lot more precision. Time. You can estimate time if you wanted to see how long it takes you to walk across the room or something by counting 1 Mississippi, 2 Mississippi. And I don't know, I sort of guesstimated. Maybe that's plus or minus 5 seconds every minute that you're counting. But that's a free method, and it's cheap and it's not very accurate. Well, if you'd like to get some accuracy, I don't know how much these cost. I tried to look up a price to find a good price. You could buy a cesium atomic clock that's used by the National Institute of Standard Technology and the U.S. Naval Observatory in Washington, D.C. to track our time. And that costs millions of dollars for one of those devices. And it's accurate to 1 second every 300 million years. So that is very accurate. And that's the time that we use in the U.S. to standardize everything. The question is, why would we spend millions and millions of dollars to worry about a second gets lost every 300 million years? Well, I'll give some bonus points to anybody who can find a good answer to why we would care about measuring time to that low effect. Because it turns out it is very important. So if you post a good example up on the internet of why you do that, you can only post one example, but other people post other examples. Look up a little bit of reading on cesium atomic clocks and why they're important. Percent error. All right, if we have a measured value versus a design value, or in a lab, if we have a theoretical value we're trying to measure, and we have our experimental value that we have collected, this is our data collection process. How do we measure the difference between the two? Well, a lot of times we like to see not just this. You can subtract two values, you get an absolute value. But a lot of times we'd like to have what we call a relative measure of the difference in the values, which is a percentage. All right, and we use percent error to do this. So I gave you a little example here. Let's go back to my wedding ring example. Let's say that the design was meant to be 0.020 meters or 2 centimeters to 2 significant digits in diameter on the inside. And the question is, how much larger or smaller is the ring compared to the target design value? All right, and so here's the general formula for percent error. It's the estimated value or measured value minus the actual value that your target value divided by the actual target value. You can also look at it as this, our measured value minus design value. Design value, or you could look at from this, when you're doing a lab experiment, your experimental values that you measure during the lab minus your theoretical values that shouldn't occur in the lab divided by the theoretical. In each one of these cases, you take that ratio and multiply by 100, and you get your percentage. Here's the numbers for the ring I plugged in. Be careful when you're calculating this. You actually need a set of parentheses on top if you're not careful with your calculator, or else you're going to error. You calculate this number, and it turns out in this case I have negative 15% error. And just a couple of notes that error can be positive or negative. A negative value on error means that your estimate or your measured value, your experimental value, is below the actual value that you want, your target value. All right. If it's positive, that means your measured value, your experimental value is above your target value. It's too high. So positive means your number is too high. Negative means your number is too low. Also remember to round your percent error using number of significant digits. In this case, we were using 2 significant digits, and so I rounded my final answer to 2 significant digits. SI prefixes. SI prefixes are just a way to use a shorthand notation to make it easier to read and write and talk about really, really small numbers or really, really big numbers. All right. like 0.000000001 meters. It's difficult to read manually. Right? You got to count the numbers. But another way to say it is in place of a meter or a nanometer, even easier to write a little abbreviation. You can also use scientific notation, 1 times 10 to the minus 9 meters. And scientific notation, you can actually use these types of prefixes to define our SI prefixes. So you are required to memorize the prefix names, their symbols, the multiplier values, and the scientific notation multiplier value. All right, and you also need to know how to convert and manipulate these, convert to decimal and convert back and forth. All right. So this is a table out of your book that you need to memorize, and this is the symbol we use for the prefix. That's our SI prefix. There's a name for it, and you'll notice here that we really only care about the items by powers of 3. With one exception. So I have everything here is going by powers of 3. The power of 2 here is one oddball. That's a fairly common one we end up using. But for the most part in physics, we go by groups of 3. And by the way, you can look up these numbers. This goes up to tera, but they go up, up, up from there, and down, down, down below pico as well. And you can actually, your book might have some more values listed, or you can go online easily and see that these are predefined quite a ways up and down for large and small numbers. So, but basically the way we use these SI prefixes, if you see kilometers, for example, the word kilo literally means multiply by 1,000. So I can take 10 kilometers, for example. I can actually take this K and replace it with times 1,000. So I get 10 times 1,000 meters, which is 10 times 1,000 is 10,000 meters. All right. Let's say I have a stopwatch, so a very accurate stopwatch that maybe measures 52.4 microseconds. Well, what does that mean? Well, micro means times 1 over 1 million. You can plug that in there. Or I think it's easier to use these base 10 powers here. I've got 52.4 times 10 to the minus 6 meters, or seconds, sorry. So simply do a one-to-one replacement. Take the micro out and put 10 to the minus 6 in, because that's what it tells you to do. And if I take 52.4 times 10 to the minus 6, what does this mean as a decimal? Well, minus 6 means the number is tiny. I'm going to make this tinier by 6 decimal places. So I'm going to take this 52.4, I'm going to move the decimal place over 1, 2, 3, 4, 5, 6. There's my new decimal place. I'm going to put in a 0. So I'll get 0.00000524 seconds. That's how you can write. But you need to memorize this table. The first time I give it to you in order, the second time I'll give it to you in mixed up order. So we just covered some number formats. Plain old decimal numbers are just the numbers you grew up with. All right. You'll notice in physics, though, we tend not to use fractions so much. In formulas and stuff, might have a fraction. We'll have kinetic energy equals 1/2 kx squared, for example, or 1/2 mv squared. But when we actually crank out the numbers and the values, we tend not to use fractions at the end. In the same sense, we may have a pi in an equation, but when we come out with a value at the end, we tend to replace the pi with its equivalent of the decimal, rounded properly based on our number significance. Scientific notation. We know scientific notation. Here's a couple of examples down here. So I have like negative 1.23 times 10 to the positive 2. Don't ask me how I get a negative distance here, but that's my example. I'm sticking to it. If somebody can tell me an example where we have negative 12,300 feet, how can we have a negative distance reading? I'll give you one bonus point for this. This is an easy example for this. The number format, the format that we use for this, I put it in blue here. We have a positive or negative sign. We have some number. We have a multiplication sign times 10 to some exponent with some units after that. Don't forget to put units on numbers. This number has to be between 0 and 10. So you can't be 10, and you can't be 10.1, 10.2, it has to be 9 point something at the most. And we can't have a negative number. We can't, well, actually, we can have but I can't be like 0.3. 0.3 is not, I'm sorry, this should be a 1, greater than 1. So we've got to be greater than 1 here, so greater than or equal to 1. So I can have 1.00, but I can't have 0.3, for example. So sorry, there's a little error on that. So you've got to greater than or equal to 1 or less than 10. The exponent must be an integer. So in other words, 0, 1, 2, 3, 0, negative 1, negative 2. So I gave you a couple of different examples here. Negative 1.23 times 10 to the positive 2 feet. What I do with that positive 2, I take the decimal place and shift it over twice. Sorry, this is and so I have negative 123 feet. So sorry about that little error there. My next example, I have a number of grams here. So I have 7.082 times 10 to the minus 4 grams. And minus 4 means I'm going to go 1, 2, 3, 4 to the left to make this a very small number. If I do decimal point, so I have a 0 point, and I'm going to fill in some zeros here. 0, 0, 0, 7.082 grams. You can see that's just a very tiny number of grams. For SI prefix notation. And remember what I said, SI prefixes, in order to work these out, all you're going to do is replace that prefix with the value that you memorize. I tend to use the values that are the times 10 to the power type of values. And our format is we have some number, we can have a positive or negative sign up front, and then a space, and we put the SI prefix, and we bump it right up against the units. All right. The number that we have here, and that should be a 1, is greater than or equal to. So we should have a 1 is greater than or equal to the number is less than 1,000. The question is, up here we have greater than 10. Why do we jump up to 1,000? Anybody can explain why that is a good bonus points. And once again, the first person to post that, the correct answer on the Facebook page can earn those bonus points. The exponent. There is no exponent. What am I talking about? Sorry, this is a couple page. Your SI prefix comes from your list of SI prefixes. And there are additional SI prefixes. You probably memorize, like King Henry doesn't drink chocolate milk or something like that. There are additional ones, but like I said, for physics, we use the ones that are multiples of 3s plus the centi, which is to convert these SI prefixes to decimals, literally you take your SI prefix, take your letter of the alphabet that they put in there for you, and you replace it with its multiplier value. Then you shift the decimal places. So I've got 49.2 kilometers. The K is my SI prefix. Literally, I take this K and I replace it with that. Here's my replacement right there. Drop it in instead of the K. And then I just do the math. Times 10 to the positive 3 means, well, positive 3 means a big number. I'm going to shift the decimal places over 3 places to the right. So 1, 2, 3. Fill in the zeros with the empty bubbles here. So I've got 49.2. 1, 2, 3. 1, 2, 3. Sorry. And here's my new decimal place. I got 2 zeros over there. So I got 49,200 meters. A couple more examples. These are on a worksheet that you have. Let's convert these numbers to the other formats, and then we can also round these to 2 significant digits. I'll hold off on rounding until then. All right, let's go decimal and let's convert to scientific first here. And so, well, we need a number that's greater than or equal to 1 or less than 10. 70 is too big, so we're going to have to move our decimal place over by 1. So we're going to have 7.025 times 10 to the what? Well, we moved it over 1 spot. So it's going to be 1 But is this 70? Is that a big number or a small number? Well, we're talking big or small compared to 1 to 9. This is bigger, so it's going to be +1 for our exponent. When we have digits, don't forget the units. Let's round this now to 2 significant digits. Those are the 2 digits, and we're looking at 2 rounding. So it's going to end up being 7.0 times 10 to the power of 1. If you wanted to go into SI prefixes, if you look back at your table, there's a little trick here you follow. All right, in the SI prefixes, we have our decimal places are shifted in groups of 3. All right, and so for 70.25, we've got times 10 to the 3rd, times 10 to the 6th, times 10 to the 9th. That's going to shift in groups of 3, or we can shift the other way. Well, in this case, our standard for this is we have to have a number up front that's between 1 and 1,000, and we already have a number that's between 1 and 1,000. So really, there isn't a SI prefix that we'd like to convert this to off our table of values. If I was using the King Henry doesn't drink chocolate milk methodology, I could actually use deca and call it 7 deca inches. But our groups of 3 methodology uses 10 to the 3rd. I'm not going to change it. I'm just going to leave this at 7 inches. 2.99 times 10 to the 8th meters per second. This is actually what we call this is the speed of light in a vacuum. And we use the letter so small c for that. So c equals 2.99 times 10 to the 8th meters per second. To convert to decimal, what I'm going to do is I'm going to take my 2.99, and then this tells me I'm going to shift my decimal place 8 spaces, and this is a positive number here, 8. Positive numbers are really, really big numbers. And 8 is positive 8. This is a big number. So I'm going to move my decimal place to make this a big number. 1, 2, 3, 4, 5, 6, 7, 8. There's my new decimal place. Fill in the zeros. And then I'm going to clean it up a little bit. So I've got 2, 9, 9, and 1, 2, 3, 4, 5, 6, and I'm going to add in some commas here. All right, so it's 299 million meters per second. Now, I had to round it to 2 significant digits. Here's my 2 digits that I'd like to round to. My 9 is my rounding digit, so it's going to round. The 9's going to add 1 to this on here, which will add that, so we'll get that 30. So 300 million. You round it a little bit. Meters per second. So that's the 2 significant digits. What about in? I'm going to take this value, this decimal value. I'm going to use that to go to SI prefix. Now watch how I do this. All right. This is 300 million meters per second. All right. If I were to take my decimal place and move it over by 1 group of 3, that's a 10 to the 3rd increment. That would be kilo. So if I move my decimal place right there, I got kilo. But I still have a number out front that's much bigger than 1,000. Remember, our value, we want to get our ending value to be 1 in 1,000. So if I bump it over again, well, this bump I'm doing is times 10 to the 6th. So bumping it over 6 units, that's going to be, so this was kilo, this is going to be mega. And now I have a number up front that's down to 300. So if I'm moving this over in groups of 3, we're doing 10 to the 3, 10 to the 6, 10 to the 9, and so on and so forth. We keep on bouncing it over 3 at a time until we get a number up front that's between 1 and 1,000. All right, so I end up with 300, and moving it over 6 spaces that's times 10 to the 6. And so this 10 times 10 to the 6 is mega meters per second. Now we're going to do the opposite. Let's take 4.7 microfarads. And remember, farads is this capacitance units for electricity and capacitors. So micro, if you look on your chart, I'm going to do a straightforward replacement. Micro means to replace it with times 10 to the minus 6. By the way you write this letter micro, this is a Greek letter of the alphabet. And it's sort of like a U, but it has a tail up front. The way you write this, you start down at the bottom of the long tail, you come up, and then make a U at the end of that. And there's your U. And that's spelled in English MU for mu. All right, so we've got 4.7 times 10 to the minus 6 farads. All right, now I need to convert this into a decimal. All right, so I'm going to shift my decimal place over for my 10 to the minus 6. Now, I'll do that over here to myself. 4.7 times 10 to the minus 6. Minus 6 means it's going to be a very small number. So I'm going to move my decimal place over six places to make it a small number. So 1, 2, 3, 4, 5, 6. There's my new decimal place right there. And I'm going to fill in leading zeros in front of that. So I'm going to clean this up now. 0.1, 2, 3, 4, 7 farads. There's my answer. All right. What about rounding to 2 significant digits? Well, we already have 2 significant digits. We're done with that. How about scientific notation? Well, let's be smart here, and we should recognize over here that we've already got a number up front here that's between 1 and 10, so that works fine already. So we've got 4.7 times 10 to the negative 6 farads. That's already done. So over time, people developed units and standards for measuring these units to make it easier to trade is the key reason probably. For example, if you go to market to buy something, you want to have a common standard of measure, so it's easy to know if you're not getting ripped off by the person trying to sell you something. All right, so a pound of cheese at one place should equal a pound of cheese at another place. Over time, we have set up an international system of units we call the metric system. But it's also more formally known as the Standard International set of units. Unfortunately, the U.S. government only voted to, back in the 70s when I was a kid, they've had an opportunity, and they've had opportunities since then to formally implement the metric system throughout the U.S. and get rid of our old system of inches and pounds and things like that. But unfortunately, here we are, years and years later, and we're still using U.S. customary units throughout the U.S., which is really, as you're going to find out, really a pain in the butt, and it's unfortunate because it creates a lot of work for us, and it creates the opportunity to make mistakes. The fundamental physical quantities, we have 3 types of quantities that we can use to measure any type of unit. For example, force units, for example, aren't listed here because they are combinations of these 3 units. And these 3 physical quantities that everything else is comprised of are length units, mass units, and time units. And I've highlighted in red what our SI, we have standard international units are meters, grams, and seconds. And in terms of measurements, we tend to use a certain size units for everyday measurements. And I put those, highlighted the ones we tend to use in red. Meters, kilograms, and seconds are the typical ones we use in fitness. But kilometers are also SI units. This has a prefix that's 1,000 meters. This is a 100th of a centimeter. We've got seconds, minutes. Minutes are 60 seconds, and so on and so forth. For our U.S. equivalents, the rough equivalent to a foot, to a meter is a foot. You could say it's a yard as well, but we kind of use feet in physics, not yards. We don't really use mass units in our U.S. customary system. And our time units that we would use are just like the metric system. Everybody uses seconds, minutes, hours, etc. We tend to use seconds in physics. All right. So I sort of call these our room size units that we use. So our standard international units, our SI units that we use at our room size are meters, kilograms, and seconds. Right? MKS, that's what that stands for. So we tend to use that. And remember, by combinations of these units make up every other unit known to man. Right? And U.S. customary units, we tend to use feet. For kilograms, we don't have a mass unit, so we don't have them in seconds. So we use feet in seconds or meters, kilograms, and seconds typically in our classroom. So what do we use for mass units? We don't. And what's the difference between mass and weight? We'll talk about that later. For very, very large quantities and very, very small quantities, well, use the SI prefixes to make it easier to write those. Now, you are required to memorize a number of basic conversion units because, unfortunately, because we didn't adopt the metric system for folks in the U.S., there's not many other places that have to do this. We're the holdouts here. Some people are better than anybody else. So something we're not doing something better. It's just dumping to do it, but we're stuck with it. So we got to pay the price by knowing how to use conversions. You go to Europe, nobody has to memorize these things. All right. So meters to feet, and I'm going to give you these numbers and round it to 3 significant digits. You can look these up. You can look up a good online calculator, for example. Or if you look at your cell phone, they probably have a calculator or your TI. 1 meter is actually 3.28 feet. All right. 1 inch is 2.54 centimeters. Remember, we're going through 1, 2, 3 significant digits in each one of these. You need to know these pretty good, guys. 1 mile is 5,280 feet. That's actually 4 significant digits. And that's a definition, 5,280 feet a mile. Our mass to weight conversions. This is only applicable on Earth. 1 kilogram is 2.20 pounds. Okay. Time. And these ones you should know already. 1 year is 365 days. To 3 significant days. Now, in reality, we know we've got leap years and things like that, which is about 365 and a quarter days per year, but it's actually a little bit off of that. So you have leap years, leap hours, leap minutes, things like that. But for our sake, 1 year is 365 days. 1 day is defined as 24 hours. In reality, it's about 4 minutes less than that, but I told you that. If you look at the sun and stars, it's a little different. 1 hour we've defined as 60 minutes. And these are actually exact conversions. So 60.000 repeating minutes. 1 day is 24.0000, the standard day that we use. 1 minute is actually 60.000 seconds. So on these, I'm only showing 2 digits, but these actually have technical and information digits in these definitions. Okay. Gallons, quarts, pints, cups, fluid ounces. This you probably know, and you might have remembered seeing something like this. I'm going to draw a little picture down here. Maybe on the back of your page you can draw a big one of these. So we've got 1 gallon. So draw a huge G that makes is the full size of your paper. These things are going to get tight here pretty quick. 1 gallon is comprised of 4 quarts. All right. 1 quart has inside of it 2 pints. All right. So 1 quart is 2 pints. 1 pint has 2 cups. All right. So 1 pint has 2 cups. 1 cup has, now, you can see this, and if you drew this on your page using a sharp pencil, inside the cup, what you do is you write a number 8 inside of there. 1 cup has 8 fluid ounces, so I'd have in each side of these cups an 8. And then what you can do is you can take a look at this diagram, and you say, all right, well, how many cups are in a gallon? Well, I've got 2, 4, 6, 8, 10, 12, 14, 16 cups. All right, you can count out. How many pints in a gallon? Well, I've got 2, 4, 6, 8 pints in a gallon. How many pints are in 2 quarts? Because we have 2 quart containers all over the place. That's 4 pints. How many cups are in 2 quarts? Well, 2 quarts have 2, 4, 6, 8 cups. And so it's a nice little conversion table. This format, visual format. 1 gallon is, and you've got to double check me on this. It's either 3.7 or 3.78 or 3.79 liters. So somebody double check me on this. I think it's 3.78 liters. If I'm off by decimal, somebody correct that, please. A liter is 33.8 fluid ounces. And the reason I know that is I look on a liter bottle of water or something like that, and it gives you the conversion factor. So look around you in real life, you can see these conversion factors. A liter has how many milliliters? Well, a milliliter is 1/1000th of a liter, so there must be 1,000 milliliters in a liter. In the same sense, it turns out that a cubic centimeter equals 1,000. A cubic centimeter, there's 1,000 cubic centimeters in 1 millimeter. And we've got 1,000 cm cubes, a centimeter cube is cubic centimeter. All right. It turns out that these values come from water. All right. Originally. All right. So it turns out if you take water when it's densest form, which is at 4 degrees Celsius, and you actually have this row of values on your next page. So if you have water at 4 degrees Celsius, it turns out that if you were to take a little cube that's a centimeter by a centimeter by a centimeter and fill it with water and take the mass of it, so 1 centimeter cubed of water, it turns out it has a mass of 1 gram. All right. Okay.